Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Next Tuesday, May 15th, the TWiML online meetup is back. Our main event will be a presentation by Santosh GSK on the paper YOLO 9000, Better, Faster, Stronger by Joseph Redman and Ali Farhadi. We'll also discuss the landscape of object detection, the current state of algorithms in that space, and the challenges ahead. If you aren't already signed up, head over to twimlai.com/meetup to register. See you there. And event season continues. Today and tomorrow, I'll be at Figure 8's Train AI conference in San Francisco. I'll be podcasting all day from the event, so if you're attending the conference, stop by and pick up a sticker. It's not too late to use our TWiML AI discount code if you'd like to attend. In this episode, I'm joined by Jose Hernandez-Orallo, professor in the Department of Information Systems and Computing at the Polytechnic University of Valencia, and fellow at the Leverhulme Centre for the Future of Intelligence, working on the Kinds of Intelligence project. Jose and I caught up at NIPS last year after the Kinds of Intelligence Symposium that he helped organize there. In our conversation, we discussed the three main themes of the symposium, which were understanding and identifying the main types of intelligence, including non-human intelligence, developing better ways to test and measure these intelligences, and understanding how and where research efforts should focus to best benefit society. All right, let's do it. All right, everyone, I am here at NIPS in Long Beach, California, and I have the pleasure of being seated with Jose Hernandez-Orallo, who is a professor at the Universitat Politècnica of València, and is currently on sabbatical and visiting at the Center for the Future of Intelligence at Cambridge, UK. Jose, welcome to This Week in Machine Learning and AI.
Thank you for having me here.
Absolutely. So why don't we get started by having you tell us a little bit about your background and how you got involved in the machine learning world?
Well, it's a long story probably that many people in the area would share. As a child, I had my first computers, and sometimes I thought, how can I make this computer think? And at the times I had, well, probably it's not very common here in the States, but in Europe there was this ZX Spectrum, which is kind of a Commodore, the early computer, the early personal computers you have.
Like the Sinclair?
Yeah, Sinclair.
Yeah. Oh, okay.
I had that one with 48 Ks of memory. and at some point I started to play with some kind of basic ideas of logic, because you have that at high school and think, okay, this is about thought. And then, well, even I just played a little bit with kind of probabilistic versions of that. Now it's completely naive from the point of view of well, you know, the things are much more complicated than that. But you try as a teenager and all of that. And then, well, because of all of that, I studied computer science. But at some point when when I completed that, I felt that what I really liked was AI. That, of course, I was from the beginning, but I didn't see that much AI. Just one subject during a 5-year degree, and I was like, how can it be that you do computer science? No machine learning at the time. It was the 90s.
Right.
So, and I decided I have to do a PhD. Well, at that time, it was an MSc and a PhD on something different, more AI. It wasn't that easy to find something. It was all about these expert systems, and I said, this is not exactly AI for me. This is, and at some point I did a PhD on something related to. I started with deduction. I thought the reasoning was a lot about logic and all of that, and at some point, no. This is more about inductive inference, about learning. And then I moved a little bit to machine learning at some point. Then when I started as an academic at some point, I was really concerned, and that was from the beginning, about how to certify at some point that the system has some capabilities, or how you would say that the system is able to do something.
Okay.
So that's some kind of evaluation of these systems. And of course, at that time, people already knew about the Turing test, and I was also interested in psychometric tests.
Okay.
I'm talking about 20 years ago, so it's a long time.
Okay.
And then, because you at that time, machine learning started to flourish with applications. The terms data mining became fashionable at that time. And I also worked on building different kinds of classifiers. I was involved in ICML for some periods in terms of trying to submit papers. So that's basically a traditional, let's say, a career in trying to get into the field of machine learning in the 2000s. And then at some point, about a few years ago, I recovered some of these ideas because I was working on evaluation of classifiers.
Okay.
So things like ROC curves and how to evaluate a system for a range of contexts, rather so related to cost-sensitive learning and things like that. And I said, okay, but some of these ideas could be linked to the evaluation of AI as well, and how to evaluate some other more general systems. And at some point, I started to work on this area that I call AI evaluation. And I saw that there was a lot of things to do there. It's perhaps not an area where people prefer talking about building things. And when you say, no, but I like to evaluate what you do, is that, well, you are on the other side. It's like you are not an engineer in AI. But I thought that this was really important, and whenever I talk to people, we need to know where we are, where we are going, so it's important we have very good measurement instruments, and at the moment we don't have very good instruments in AI, because it's evolving so fast, and we are also focused on particular challenges and tasks that we are not really sure whether our systems are really progressing. We have that feeling, and of course, there's a kind of objectivity there that our systems are much better now because we are able to solve more. But at some point, I said that there's a gap here, and I tried to recover some of the old ideas with new ideas, tried to see what people were doing in terms of evaluating not only machine learning, but AI in general, also robotics. And I started to work on these areas. And then about 1 year ago, I wrote a book about this. I've been involved in the organization of several events around AI evaluation, so all of these things. And now I'm here the last year at this Center for the Future Intelligence in Cambridge, that they're doing, which this idea of AI evaluation goes well with some of the general objectives of the center. And basically, I'm still really, really enthusiastic about machine learning and AI and see what's going on.
Awesome. What's the title of your book?
Well, the title is The Measure of All Minds, Evaluating Natural and Artificial Intelligence. So it covers AI evaluation, but also it puts that in the context of how natural intelligence is evaluated. Animals, non-human animals, and humans. So a little bit of animal cognition, how tests that you can use, for instance, for development in children, or tests that you would use to test or maybe IQ tests. What's the relation between IQ tests and what we are doing in AI? And then the first answer is perhaps nothing. But there's something that you scratch a little bit on the surface, you find connections. And I think these interesting, because some of these connections are developed in the book, for instance.
I would love to dig into that in a little bit more detail. But first, I'd like you to describe the symposium that you helped organize here at NIPS, called the Kinds of Intelligence, right?
Yes. So it was around a project that we have at the Center of the Future of Intelligence in Cambridge, UK. This project is called Kinds of Intelligence. So at some point there was a suggestion to propose a symposium on some of the ideas of how to characterize the different kinds of intelligence that we know of at the moment. Not only human intelligence, but also non-human animal intelligence, natural intelligence. And how to locate AI in this landscape of intelligence. So that was the original idea of the symposium. And then at some point we developed that idea into 3 strands. The first strand was to understand this space and to see where AI is just represented as a subset of human intelligence, or something completely different that is taking us to different places. So trying to analyze this landscape a little bit from different perspectives, and we wanted to have different perspectives from animal cognition and from human cognition as well, for human intelligence and development. And the second strand was about how to test all of this. And of course, I had some influence in having this strand in the symposium. It was, okay, now we have this landscape, but how can we locate where we are?
Right.
And so we are moving in some direction, but can we say, okay, what are the dimensions of this landscape, and how can we certify that the system is moving in that direction? And the third one was, okay, if we are able to answer all these questions, which of course sound very abstract and challenging, the third question is, now that we are able to understand this landscape where we are, the question is where we want to go. And that was the third strand of the symposium, about what are the priorities for society, and whether these priorities we are perhaps, I wouldn't say the low-hanging fruits, because some of the recent challenges are really, really challenging, but sometimes we are motivated by things that are doable with current technology, rather than perhaps aiming at the really important problems, because you're not going to have a success in a matter of 1-2 years. So it's more like a long-term project that perhaps academia or even government can be interested, but perhaps companies. Well, this is changing, because the tech giants are also interested now in long-term goals. But all of these, and also some areas that we might reach at some point in the future, perhaps even in the near future, that are perhaps dangerous or unethical. But if we don't know where we are, it is very difficult also to assess the progress and the directions that we want to take. So we have that, and we, in the end, yesterday we had a fantastic lineup of speakers.
I saw that.
Yeah, from different areas. So
it seemed very interdisciplinary, very diverse in terms of the viewpoints that folks came from.
Yeah, we had people from animal cognition, from human intelligence. We had people from AI, from different perspectives from AI. People perhaps more in favor about a more orthodox approach to AI, where you would like to learn from a lot of examples, more in alignment with NIPS. People a little more contrarian to this view, where what about the learning more human-like, or more with a few examples, or more hypothesis-driven rather than data-driven. And we had a very interesting discussion in the second session about this, different perspectives. Also, we had people from the first session coming and asking questions to the people of the second session. It was very active. And the third session was a little bit about this society and some of the risks and some of the things that people are talking that we are going to see in the future. Like at some point, the discussion, it was at the right moment also to talk about, at some point, things like corporations having a lot of power. And there was a moment where there was this link about AI in the future could resemble some of the corporations that we have at the moment, or that we have had in the past 2 centuries, and they have a lot of power. So that perhaps we can link some of the risks to some things that we have already seen. So not everything that is coming is new in terms of the effects on society.
Interesting. Maybe we can take these 3 strands in turn and spend a little bit of time kind of having you characterize the landscape before diving a little bit deeper into the measurement and your research in that area. And then we'll finish up with some of the directional stuff that you discussed. So what does that landscape look like? How do you characterize the way folks are thinking about the kinds of intelligence?
Yeah, that's a really challenging problem because the first thing is we disagree on our notion of intelligence. Some people even say that the term intelligence should be eliminated from our discourse, and we should only focus on or even just use the word learning and forget about intelligence. Some people's because we have these 2 different views of intelligence. I would call one extreme is we negate that there's such a thing as intelligence. And some of these people, perhaps you can also have some these people from even from machine learning saying we have the no free lunch theorem. So even if you design a system to solve this problem, there's some other problems for which there are other systems that will be optimal for these problems, but not for the first problem, and the other way around. So this idea of just having more general systems or more intelligent systems is nonsense. Well, I would argue against that. But then you have the other extreme.
It seems like, being intelligent is very different from being optimal at everything, which is kind of what this no free lunch theorem seems to argue against.
Yeah, well, I think that's assuming that our world is random in a way. You have this block uniformity as an assumption, which is, well, a special case is that the data you receive is random. So it just says, if that's the case, well, the theorem is a theorem, that's a proof, and you say, okay, so any machine learning algorithm will be equally good or equally bad at. But the thing is, the assumption is just assuming something very, very strong. That basically our universe is completely chaotic, and it's not like that. There are patterns,
right?
And there are patterns not because the laws of physics. There are patterns because what we receive goes through humans, animals, devices. So, not just to explain this a little bit more technical, when you have a Turing machine or any machine. It doesn't have to be a Turing machine, but just any machine, and you put random inputs. What you get as an output is not random at all.
Right.
So what we see in our world, because it's just going through all of these filters, and these filters are machines in a way, that it's an animal, or it's a thermostat or something like that. What you get as a result has patterns. And then you can explore these patterns. And if that's the case, then the assumptions for the no free lunch theorem don't hold in that scenario. But well, that would be like sometimes it gets a little bit philosophical, that question. But that's one extreme. So you have like infinitely many intelligences, and this links a little bit to psychology, where you say, okay, there's not such a thing as intelligence, and you will have just the multiple intelligences theory,
right,
where you will be good at this, but you're not good at that. The other extreme is there's only one single intelligence, and we hear that occasionally, especially for some of these discussions about superintelligence. And people think, intelligence is something monolithic, and even some people try to assimilate intelligence in humans with IQ values, which is, of course, a simplification. And in psychometrics, people will say, no, this is just an indicator that it's useful to predict this and that, but you can't assimilate that to intelligence. Not people in. So the idea is you have to infinitely many intelligence in just one. Perhaps the virtue here is to think that intelligence is something with structure. So you can think as perhaps something like a general intelligence, but is related to some other abilities. Until you go down, you can see this as in a hierarchical well from the top, where you would have something like a general ability or something like that, or more. And you go to some kind of skills until you reach the bottom, and you have a very specific ability, a very specific task. Yeah. So you go from very specific tasks, you aggregate tasks into, so you put, let's say,
tasks, skills, general intelligence.
You have these, you can have many levels as you want.
Sure.
And that gives you a structure.
Okay.
So when we were, to your question, going back to your question about the landscape of intelligence, that's one way of looking at this landscape of intelligence. So we can just look at this landscape at the bottom, and we would have no structure. So there's no interest in this landscape, because we will have, okay, I'm able to solve this task, and I'm also able to solve these tasks, and these tasks are important commercially or whatever. That's interesting, but this is not going to give us a hint about what if I give you this new task? Can you tell us something about your system solving this task?
I mean, a lot of the research that we see today is kind of predicated on an assumption that if we build towards very task-based intelligence, that'll help us understand and get towards a general intelligence. I'm thinking of things like AlphaGo, right? Maybe task is too limited for what it's doing, but it's solving a very specific problem. But the only reason why they're doing that is because of this hope that it'll get us towards a higher level, more general intelligence.
Yeah, I think that the program is that they are having, for instance, in DeepMind with Alpha, AlphaGo 0, and Alpha 0. We had that talk yesterday. Damien gave an excellent talk yesterday, and people were talking about Alpha Star at the end of the session. He made a very good point in one of the questions about, okay, what we are interested in, perhaps we have to put a lot of bias to solve alpha, there was a discussion about, we'll call it bias or knowledge, or to solve AlphaGo, then and human knowledge, we can remove that and call it AlphaGo 0. Still, there's some knowledge or something. You have to put the rules of the game, for instance. But then there's a third stage that you can even make this general enough to cover some other games. And then you have this Alpha 0, which is... So this line of progress that we see is really interesting because you're going for a very specific task, using a lot of knowledge, which is very difficult to adapt to just a small change of that. And you need a lot of effort to succeed for that task. To a system where you can have, even if you have to put still some knowledge, the rules and that, the system is able to do much more independently, much more autonomously. And then you have a third step in this progress where you have a system that is more general. Still, this system is only able to solve some kind of board games if you give the rules. But that sounds amazing in terms of just 10 years ago, that you could have just one single system, just give the rules of any board game, and perhaps we don't know because you need to do all of the experiments, but perhaps for a wide range of board games, you have a system that is much better than humans for all of them. This goes in that direction of bottom-up, which is a very interesting, so you're getting more general. How general you can get, how interesting it is to have something like a very general system without bias at all was one of the topics for discussion yesterday. I think that in some case we have this discussion about the kinds of tasks we are interested in. And some people say we are interested in those tasks that humans are good at. But perhaps there's some other tasks that people are very bad at, and they are really, really interesting as complementary to what we're doing. So it's not easy to map this space, but I think that's perhaps a very important challenge. And I wouldn't say that we are playing with fire, but we are doing a lot of great things without really understanding where we are, and perhaps just trying to analyze the connection between tasks, what the tasks have in common, because we say, okay, chess and Go have something in common. But can we extrapolate what Alpha Star is able to do with robotic navigation? You say, it's a completely different system. You can reuse some of the ideas, but of course this system is not meant to solve this kind of tasks. It's not general enough. But the human, even if it is not that good, is not optimal for any of those tasks. So we go to this idea of intelligence being second best at everything. You don't have to be the best. And we move away as well from this idea that your child is a genius at something, but very bad at all the rest. So intelligence is something in the middle. You're not the best for everything, but also it's not this idea you are very good at just one thing, because you wouldn't call that intelligence. That's the narrow approach to AI. So I think this is basically the interesting part, to categorize what it is, what we have in the middle, this kind of a structure of intelligence and relation between tasks, and how we can extrapolate from what a system is able to do to other tasks. And it's a question of applicability in machine learning and AI. Sometimes, and what about, I have this task, can I use your technique? And you have all these discussions you will need to change. It's not only that you have to train all the hyperparameters, sometimes you have to change the architecture completely. And we have all of these discussions about generality in AI, in machine learning. And so this landscape tries to give some kind of conceptualization about this. Of course, I don't think there's going to be one way of looking at this landscape, but if there are different proposals, and in some areas at least there's some, you can say, okay, what about a number of examples that you need, a training curve, you can put some dimensions and you can plot some systems according to these dimensions. You say, okay, I'm here and I want to go there. And humans are perhaps at that corner. And we know where we are, but we need to do more of this. And that was one of the motivations of the the symposium and also some of the projects that we're having at the CFI as well.
And so where does measurement fit in, and how has that led you to a specific set of research that you work on?
Yeah, and I think measurement is everywhere in science and technology.
Sure.
So for me, it was a kind of surprising to say, okay, how much we are progressing in AI, especially and in machine learning, and we don't have very good measurement tools. Of course, we have tasks, and we can say, okay, accuracy or some other metrics.
Task performance, right?
Yeah,
metrics,
with different, but
where's that lacking?
Yeah, the thing is that the question about measurement here is measurement for which tasks. Mm-hmm. And that's the main question. Just for one single task, you can put some kind of a metric of performance, and this is going to work well. And there's no objection if you have an utility function or even just some cost function, money associated with a task. That's perfectly okay. For instance, self-driving car. I think that's complex to find a good metric, but it's clear that you can say, okay, these routes are more frequent than others, accidents, speed, right. Things like that. You can put all of these in a formula, right. And say, yeah, I want to maximize this. Yeah. But for some other systems, we want them to be more general. We don't have it. We want a system that has very good verbal abilities. This is too abstract. Right. We don't really know how to do that. Well, so we can have a good translator. Even for machine translation, there's a strong debate about the evaluation metrics, about whether what you get is readable or you get the idea, or what kind of mistakes are worse. Because we are entering an area where we have to talk about meaning and interpretations, human interpretations, about whether I think that this is a good translation. Of course, you can always say, okay, I can just perform a lot of translations and have a human assess these translations from 0 to 10 or something like that, and you can have a metric. But in that case, you are not sure what you're really evaluating. Right. In contrast with, for instance, the self-driving car, which is kind of objective in a way. So we find that even in robotics, there were some discussions. For instance, there have been several European Union projects on robotics, and okay. One of these big meetings, there was someone who said, "Okay, we are progressing. But can we really measure that? You say you solve this task, but we still have this task without being solved, and the system solves this task, but not the other task. So we have more because we solve more tasks because we have more robots." So more specialization, but not really, right. Because we have one robot that is able to solve it. And in terms of efficiency and economy, what we want in machine learning is to have systems that are able to solve a range of tasks without a lot of tweaking and tuning and changing architectures, because that takes a lot of effort from teams, and we want to have systems that are easier to develop, that they require, for instance, less data, all of these things. So having metrics around all of this is going to give us a better assessment of whether we are really progressing, and especially at conferences or when we have one of these breakthroughs in AI, really understand whether this is a great breakthrough. Mm-hmm. For instance, when I saw AlphaGo, I was impressed, like everybody. I was, sure. Come on, this is so good. But I was, for instance, the other day, I was more impressed about this system just learning Go chess and this Japanese chess as well. And I think for me, this is even more important than what we saw 2 years ago. Right. But this is my view. And at some point, we would like to have some kind of metrics where we can say, okay, can we say something about what these systems are able to do, and put that some kind of even quantitative assessments of what, talking more in terms of skills and abilities rather than a specific task. So that's basically the interest in measurement, and now all of these new trends about evaluation using video games. I think this is really, really interesting. But again,
describe that work. Is that like related to the reinforcement learning type of work?
We are having many platforms For instance, we have Microsoft Research launched Malmo, Minecraft, which is a Malmo platform. We have Good AI released this. Now it's integrated in the AI universe.
OpenAI universe.
OpenAI universe, and then you have DeepMind with also the evaluation platforms, and also some competitions using video games. And we also have the Atari games, and all. So we, in a way, we see many evaluation platforms where we have a range of tasks as different video games, and we see that our systems have been evaluated according to how well they behave for this range of games.
It seems like relative to some of the, relative to more kind of higher level or conceptual definitions of intelligence, performance on a video game is more akin to evaluating a self-driving car. What's my score? How fast did I do it? How many times did I die? Things like that. What makes these video game platforms interesting for the types of measurement that you want to get to? Yeah,
that's a very good question. But I think that in a way, a self-driving car is, even if it requires more technology, more different technologies than, for instance, a video game. A video game is a mini world in a way. It's an environment.
Right.
Of course, the self-driving car is an environment, but the thing is that for video games, if you just define one video game, I see no difference. Even, of course, the self-driving car is much more complex, much more interesting in terms of the technology that you need to solve it. But the good thing of video games is you usually include 20, 50, 100 video games, and then you have a range of tasks. And then we have a range of tasks, different tasks, even if they are 2D or 3D, and there are some kind of a shared input-output for these platforms. There's the kind of
So you're speaking to being able to kind of to demonstrate generalizability?
Yeah, that's the idea.
Yeah.
So you try these games to be as diverse as possible in order to show that you are able to learn this task. Then if your system is good at all the tasks, or just kind of even if it's not optimal at any of them, I think you have a kind of a general performance for this range of tasks. And the more general you make this pool of tasks, you go up in this scale from bottom task-specific performance to more kind of a skills, or maybe towards you go up in this direction of more general intelligence. And that's what, of course, you can claim that even if you take 100 games, Atari games, that's a very specific subset of all the possible tasks that you might have, and that's true. But I think you can explore these first steps from bottom up, from very specific tasks to more general. And you can also analyze all of these ideas about why is it that this system is good at these tasks but not at those tasks? And then we're like, these tasks are more about abstract thinking or planning. So we see that for us, our reinforcement learning techniques, even if we are using deep learning with them, they are not very good at generalizing for this. So they are not solving these tasks well. So we can learn much more than we've just focused on one single problem that in the end, if we put a lot of effort, we'll ace at that problem. But that perhaps how much of that effort is extrapolable to other problems, that's basically what we want. We want this generalization ability in machine learning.
Have you published any research that specifically looks at applying measurement to these video game scenarios?
I've taken two different approaches. There's the idealistic approach, which is basically going from first principles, which is basically in my book and some related publications. They say, how can we define a set of tasks that by definition are necessary to show that the system has this ability? That would be great, because of course you can say, okay, why 100 games? Why don't you use 1,000? And why are these 100 games sufficient for this? Or
so you can kind of decompose the games to map them to these set of tasks and determine this game framework's ability to even assess intelligence at all. Is that one of the things?
Yeah, the idea is that we can generate these tasks rather than reuse tasks. Some of these platforms are generating games. But if you generate a game just randomly, you get something that is completely meaningless. usually, and it's not fun to play. So you have a lot of random noise. And you have to put some structure into an environment to make it appealing for humans and meaningful also even for machine learning. So the thing is, how can we generate these tasks in a principled way so that we ensure that, and a key concept here is that you can define the notion of difficulty of this task, so you can have a scale of difficulty as well. And you can relate these tasks in terms of that difficulty and what they have in common. The problem about this approach is that you can only generate, at least in principle or easily, you can generate some kind of very abstract environments, a very simple environment. So that's one. I think that's a very good way, but perhaps it might take more efforts and more ideas just to make it work in practice. And the other one, which is summarizing some papers, for instance, last year at the European Conference on AI, we had a paper on that, and in some other machine learning conferences. It's how to use, for instance, one technique from psychology, from psychometry, which is item response theory, where you can characterize from a range of tasks. For instance, you take a competition, for instance, the video game playing competition. Mm-hmm. You take the results from last year, and you analyze, you have, for instance, 40 tasks, and you have 30 competitors. And you analyze, you just try to understand not only the performance of each of them, but you try to extract latent variables by analyzing this result matrix. And you try to analyze, okay, can I analyze the difficulty of the tasks or the relations between these tasks? Can I analyze the relation between the participants as well? And at the end, you can get, for some of these techniques, you can have something like the difficulty of a task, and then you can realize this task, according to this population of AI systems or machine learning systems, this is the most difficult task. But not because the score is 101 and the other is 80, but just how challenging it is for the systems. And you can also determine the ability of the agents. Of course, this is a simplification because you can extract 2 latent variables, but you could do 10 latent variables to be. But these latent variables explain the behavior of these systems for this set of tasks. And it gives you information for instance, the next competition, which tasks are completely, you get some other, for instance, you can extract a third parameter, which is discrimination. You say, okay, this task is completely useless. Or sometimes you have some kind of a negative discrimination. This task is performed well by the bad methods. And the other way around, they say, okay, so what's the point of having this task here?
Yeah.
And that's something inherited from psychometry. We have a question that you say, okay, good students are typically bad at that question. You remove the question. It doesn't make sense. There's something, there's a catch there or something because people get confused because otherwise you wouldn't get an explanation. So all of things help us to understand a little bit better what is going on, especially when we have competitions, when we have benchmarks. And we've also applied that to the Atari games results. And see a little bit what's happening with some of the games and the difficulty of the games, and we can have a better understanding of the abilities and the problems of current technology. Of course, this is not for first principle, this is experimental, but right. At least gives us more understanding of what's going on than just looking at the results and the winner of a competition.
Mm-hmm. So it's a set of methods for essentially decomposing these results into kind of generating the tasks themselves or inferring the underlying task and their difficulty from the results. Is that the right way to think about it?
It's a question of trying to describe the tasks and also the participants with some kind of a latent variables that you put into the models and then you estimate from the results. And you say, okay, and these latent variables, you can call them difficulty, discrimination, and on the side of the techniques, you can call that ability. These factors of variables help you understand what's going on. Is that something that you do in some other scenarios? It's nothing really new but it gives you more understanding than just looking at the matrix or just a scale that you get from the performance. Or for many of these games, it doesn't make sense to make an average of the results. Many papers you have this comparison with humans, which is okay. For instance, you have 50 Atari games and you have one technique, one machine learning technique, and you have the results for each of them, and then you have the humans, the average human. Basically, they have use or maybe on Amazon Turk or whatever they have, and they have this average score. And you say, we are superhuman on task 1, we are subhuman on task 2. Well, that doesn't say too much to me in a way, because we are not able to solve this task in terms of the human level, but we are not comparing also the number of games that we are giving to humans and the number of games that we are giving. So it's not a fair comparison in the first place. It doesn't allow us either to say there are 50 games, we are above human on 40 of them, and we are below human on 10 of them. Perhaps there's such a system, the 39-11, and it's much better because the differences are much better. So we have a lot of discussion about how to integrate things that are not commensurate in a way.
Okay.
When we put many, many tasks together.
Okay.
And all of these questions appear again and again, especially in benchmarks, competitions about people typically would like to have one kind of a single score or something like that. And looking at all the specific scores is you don't get a lot of meaning, but if you just oversimplify to a single average score or something like that, then you probably miss a lot of information as well. So something in the middle that you can summarize the behavior of these systems for this set of tasks that help us to understand whether we are going in the right direction, we are still very far from solving the problem that we want to solve, and all of these things.
Interesting. So how about quickly, kind of a quick overview of the future directions and priorities? Where did that conversation end up?
Yeah, it was a very open discussion yesterday at the symposium. Well, when you set up a session with what society needs, it's like, everyone has a say here, and we had many questions as well, and we had a panel for 40-50 minutes. It was a very long panel, a lot of things. We touched upon many, many topics. But there was this idea of having more human-like AI rather than complementary or not to what humans are able to do. I think that there's no agreement there. So because computer science and AI, one of the main goals have been automation of tasks.
Right.
So, of course, it's good that the machines are able to do things that we can't do. That's great. But we are also interested in some tasks that can be automated, and perhaps we can do some other things.
Yeah.
But, of course, you have a lot of implications about that. But this idealistic view that we want humans and machines to be complementary, I think it's very idealistic. And there's a kind of but that perhaps we can focus on these things rather than just... So human-like intelligence is important, but another way, finding things that machines can do that we can't, that is not really human-like, this is also a very good direction. And there was also some more political questions about domination, power, and, for instance, corporations and organizations having a lot of power. There was a discussion, not really in terms of AI companies and all that, which is a different debate, that we didn't touch that. But about this idea that in the future, intelligence has changed our planet. Because and having more of that intelligence or different kinds of ways of extending the intelligence that we know of at the moment is going to transform everything.
Yeah.
So we had a debate on all of these things that might be transformed. And also ethical things about, there was this discussion about bias in machine learning. So we had a little bit of everything. It was about 40 minutes of discussion.
Oh, wow. Do you know if the symposium was recorded? Will people be able to find it afterwards?
Yeah, we've been told that it has been recorded. It was recorded. There was a camera there. Probably it will take a while to have it online, but we hope that everything will be online soon.
Okay, great. It sounds like a really wide-ranging and interesting set of questions that it raised, and I hope to get a chance to take a look at it. Thank you, Jose, for spending some time to chat with us. Any final thoughts or ways that folks can catch up with you or find out more about what you're doing?
Well, we are having some probably some workshops next year, but just if you Google my name, or you will find some of the things that we are working on and some of the projects in the past years, and now with the Center of the Future Intelligence. There are many things, many interesting things going on there.
Okay, awesome. Well, thanks so much.
Thanks for having me here, and it's been a pleasure.
All right, everyone, that's our show for today. For more information on Jose or any of the topics covered in this episode, head on over to twimlai.com/talk/137. Of course, thanks so much for listening, and catch you next time.